Hi, everyone, and welcome back to the 2018 Hack Summit. We're joined here today by MacLane Wilkison, who is the CEO and co-founder of NuCypher, which is creating a privacy-preserving technology for the blockchain with the concept of proxy re-encryption. And so, MacLane, we're super fortunate to have you here. This is an advanced new technology that he's innovated for the blockchain. He's going to teach us all about it as well as related concepts. So, MacLane, thanks again, and looking forward to learning more about your technology here.
Awesome. Thank you, Ed. And hey, everybody. Glad to be here. So as Ed said, I'm MacLane Wilkison. I am the co-founder and CEO of NuCypher. Today, we'll talk a little bit about NuCypher, but also just talk about kind of privacy technology for blockchain and decentralized applications in general. But before I do that, I'll just give you some sort of context and background on myself and what we're doing at NuCypher. So we basically, our vision or our mission is that, and our belief is that privacy is obviously important to things like digital commerce, but also is fundamentally a human right. And our role or our job as a company is to build the tools that developers will use to build privacy preserving applications. So a lot of the core technology that we build on top of is something that Ed mentioned called proxy re-encryption. We also do a lot of research, longer term research into other cryptographic primitives like fully homomorphic encryption. But we are specifically focused on building developer tooling to make it really easy for people to build these privacy preserving and respecting applications, specifically for blockchain and for this new sort of decentralized computing environment. So some of our early users, people who are building on top of NuCypher, are a lot of data exchanges and data marketplaces like Datum and Ocean Protocol, decentralized databases like Blue,Zell, and Wolk. Very popular use case is this idea of patient-controlled medical records. So projects like MediBlock are building on top of this as well. And then Origin, which is the sharing economy protocol, and I believe is actually talking right after me. We're fortunate enough to be backed by a lot of the leading sort of crypto funds and traditional investors as well, like Polychain, FBG Capital, Y Combinator. So today, most of what I want to talk about is kind of just why we believe that privacy is important and sort of what drives us to work in this space and work on this technology. And then also briefly touch on a lot of sort of the basic cryptographic building blocks for cryptocurrency ecosystem, as well as I think what are some of the newer technologies that we at NuCypher are building, but also some of the other projects in the space, and then kind of where I think we are going. So I guess the first question, just what is privacy? And in NuCypher, our position is that it's not just a nice to have, it's a core requirement. Obviously, it's important for sort of just enabling digital commerce in general. You can't transmit credit card numbers in the clear. You need to have some way for those to be private, confidential, and encrypted. But we also believe it's just fundamental to protecting people's individuality and having sort of control over your own data, being able to communicate in private with your employer, with your friends, with your family. And I think there are really significant societal benefits for privacy. Obviously, the big one off the bat is just a practical matter of how we do digital commerce today. You have to have at the very least some sort of encryption in transit, so how you transmit credit card numbers to make a purchase. But I also think it's, not everyone in the world has the luxury to live in a relatively benign country where the government is perhaps pretty respective of individual property rights and things like that. And so I think privacy, and particularly the newer technologies that we're building and other projects are building, is sort of very core towards protecting against things like state surveillance or corporate surveillance. So to start, I think I'll give like a brief history of kind of where or how privacy has been viewed by society throughout history, starting with what we'll call privacy 1.0. And traditionally, it's been very difficult for individuals to exercise privacy. It's kind of been meted out by trusted central authorities, governments, religious institutions, more recently, large corporations. And we'll call that, privacy 1.0. And originally, your right to privacy was kind of defined or was a function of your individual wealth, but also your status in society. So in ancient Greece, the concept of of privacy for the average person pretty much did not exist. But if you were wealthy, you could build your house in such a way that you sort of block out outside viewers. You could create, you actually basically just purchase privacy through your social power. Later on, with things like the printing press, we decentralized access to new information. So privacy became a function of your education. And before the printing press and this sort of idea of being able to read silently, content was basically consumed in public. So you'd be dictated sort of your ideas by a clergy member or in a public square. But even with the decentralization of access, the fundamental limit was your literacy, your education. And today we've actually sort of solved a lot of those limitations around wealth, social status, or education. We have really the tools necessary to actually assert a pretty high degree of privacy. But what's ended up happening is we've kind of traded that off for convenience. So we have a lot of these large technology providers like Facebook, Amazon, Google that give us really a hugely valuable services, but in exchange, we're basically giving up all of our information to that service provider. So it's a transaction where basically they're able to monetize all of our identity information, all of our transaction information, our browsing history, our social media data in exchange for providing us this service. And I think we've, in many ways, as a society, have paid the price for that in a lot of these large-scale data breaches, which at this point are happening weekly or monthly, where hundreds of millions or billions of private records are leaked, like Yahoo, Equifax, JP Morgan, LinkedIn. It's pretty much a daily occurrence at this point. And if we think about kind of what the basic building blocks of privacy in this current environment are, basically we just have to have things like in-flight encryption with TLS or HTTPS. But because the service providers are providing that service, oftentimes in exchange for our data, all of that data that we send to Amazon or Dropbox or Google gets decrypted server side. And maybe it's okay for us to, if we set aside sort of the fact that we're giving up something that has quite a lot of value to these service providers, maybe it's okay in a centralized world for us to do that. But if we sort of take a couple steps further into the future and we project forward and say we think that a lot of these centralized service providers are going to be disintermediated, we're going to have a lot of decentralized applications in their place, having everything decrypted server side just is a complete non-starter, because that server is not a node sitting in Amazon or Google's data center. It could be an IPFS node sitting in some random person's basement, or it could be a node sitting in a malicious, controlled by a malicious nation state. So we have to have some way to have data be fully encrypted from the data owner to valid recipients and not ever exposed in between. So that's the sort of vision that a lot of these privacy preserving projects are working towards, including us. And the early blockchains like Bitcoin and Ethereum, I think, were an interesting step in this direction, but they were built in a way that sort of fundamentally placed this idea of non-censorability or integrity and authenticity above privacy. So Bitcoin, Ethereum blockchains are obviously not private at all. All of your transaction history is completely public. That's basically the way that we come to consensus on the state of a network. They are arguably pseudonymous. So in Bitcoin and Ethereum and many other cryptocurrency systems, the identity is effectively a public-private key pair. But that's not the same as anonymity, particularly in practice, because today, at least to use Bitcoin blockchain, to use Ethereum, we often have to go through on-ramps like centralized exchanges, payment processors, payment gateways, who oftentimes require things like KYC or AML. So it's actually very trivial to link balances in cryptocurrency to a specific real-world identity. We've seen that in practice. There's a company that trades a significant amount of venture funding specifically to work on this problem. So doing things like KYC, AML, and blacklisting of accounts for exchanges, for payment processors, for intelligence agencies. And it's, in practice, actually very easy to tie pseudonymous accounts to the actual real-world identities and completely de-anonymize these systems. So I think that has caused a lot of these sort of new wave of projects like Zcash and Monero to try to build privacy into blockchains. But before we get into that, sort of go over some of the major cryptographic building blocks behind existing cryptocurrencies, as well as some of the new systems that people are building. And a big one is this idea of symmetric encryption with block ciphers and stream ciphers. So symmetric encryption is this idea that you encrypt some data with a symmetric key, and you can decrypt it with that same symmetric key. So there's only a private key, and it's used both for encryption and decryption. And that was kind of sort of the first iteration of encryption algorithms. And then this idea of asymmetric cryptography came about first with RSA. And this is the idea that you can have two keys, one which is a public key, which is used to actually encrypt the data, and then another separate key, which is the private key, which is used to decrypt the data. So this makes it a lot easier to sort of encrypt data for other people, because you don't have to share this private key. Actually, in practice, that private key should only be in control over the data owner. It makes it a lot easier to transmit and communicate, as opposed to having to find some way to securely transmit this symmetric key. After RSA came elliptic curve cryptography, and this, in fact, is what a lot of the current cryptocurrency ecosystem is built on. And elliptic curve cryptography is basically a lighter weight version of, asymmetric cryptography. So it's lightweight enough to run on low-powered devices, or IoT devices, for example. Bitcoin and Ethereum actually use something called SEC-P256K1 as their elliptic curve. But one of the interesting things to note about elliptic curve cryptography in general, and also the curves that Bitcoin and Ethereum use, is it's actually not quantum safe. So it's probably not an issue today, but in the future, that'll have to be a consideration for the ecosystem generally, is if or when quantum computers become reality, we'll have to think about some pathway towards making these systems quantum safe. Cryptographic hash functions are another one of the basic building blocks. And a hash function is basically the idea of taking some arbitrary data input that could be of any size, putting it through some mathematical hash function, and then outputting some fixed sized output. This is actually basically a function that Bitcoin miner and proof of work miners do when they're trying to mine a new block. Cryptographic signatures are kind of the flip side of encryption. So if you think of asymmetric cryptography, you encrypt with a public key, decrypt with a private key. Digital signatures, you can sign something with a private key and then validate that signature with a corresponding public key. So this is useful for basically this idea of non-repudiation. So if you sign something, or if I sign something that I own the private key to, people can be confident that I was actually the one that sent that message, because I'm the only one who has the private key. I'm the only one who has the ability to sign. And then I'll briefly touch on some of the sort of historical attempts at this idea of usable encryption. So typically, when you encrypt data, the idea is you've generated some random gibberish or encrypted ciphertext. It's not usable. You can't run functions or processing against that data. You can't search across ciphertext. But in certain cases, maybe we want to obfuscate data while still retaining certain properties. So one very simple example is this idea of format preserving encryption. So let's say you have a database table of credit card numbers, but you want to encrypt those credit card numbers, but the field in that database table requires some specific parameters for the input. So in the case of credit card numbers, it requires the field to be a fixed length number or string. You can't put an AES encrypted ciphertext in there because it's too big, but you can use format preserving encryption to take a real credit card number, format preservingly encrypt it, and then sort of the output of that is the same length as a traditional as an actual plain text credit card number. There's also this idea of searchable encryption. And this is the idea that you can take some plain text and then map it to a specific token. So let's say you have a database table of names and you want to be able to search against those names. So you want to be able to search for Alice. You can tokenize Alice's name to map that to some specific token. Every time you encrypt Alice, it will map to that same token. So instead of searching for Alice, you just search for that token, and you can find it. The trade-off for this is that given you're not getting a random ciphertext every time you encrypt Alice, this opens you up to certain types of frequency attacks. So for example, if you're encrypting natural language, we more or less know the frequency that particular letters or words occur in the English language, so we can map specific tokens and deduce what the corresponding plaintext is. So this, generally, when you're sort of playing around with these usable encryption algorithms, the trade-off is they're not as secure as things like AES or SHA-SHA-20. So now going forward, I think I'll talk a little bit about some of the current projects in the space that have either already shipped and are being used in production or are shipping soon. And these are things like what we're working on at NuCypher with Proxy re-encryption, also some of the new private currencies like Zcash and Monero, secure multi-party computation and TEE. And the interesting thing about this privacy 3.0 era is that there's a lot of projects that basically put this ideal of privacy on par with the traditional characteristics or ideals of blockchain, which is things like non-censorability and authenticity. And to start, what we're doing at NuCypher is working on a technology called Proxy re-encryption. And Proxy re-encryption is a form of public key encryption or elliptic curve cryptography that allows you to basically share data one-to-many or many-to-many. So it's a nice primitive for building cryptographically enforced access controls. So if you compare it to traditional public key encryption, which is very good for one-to-one communication, let's say I have some secret message that I need to share with one of you in the audience. I can encrypt with your public key, send it across the network. You can decrypt with your private key. But let's say I need to share that message, not just with one of you, but with all 17,000 people that are watching this webinar. I'd have to encrypt that message 17,000 times, send it across the network 17,000 times. It just scales very poorly. But instead, what I could do with proxy re-encryption is that I can encrypt that message one time with my own key. I can upload it to some storage layer. This could be IPFS or Swarm or Amazon S3. And then using proxy re-encryption, I can re-encrypt or rekey that data so that it goes from being encrypted under my key into being encrypted under some recipient's key. And the special part about proxy re-encryption is that re-encryption transformation can be done by an untrusted proxy who never has access to the plaintext data, and it happens without ever decrypting the data in the middle. So it gets re-encrypted. Alice's data gets re-encrypted for Bob without the proxy or the storage layer ever having access to the plaintext data or the private keys. And we've combined this with decentralization via the Ethereum blockchain to create a threshold split key version of proxy re-encryption. So instead of having one proxy, we can split the trust across multiple proxies. We can combine it with things like smart contracts to make access conditional on certain events, like requiring someone to pay to access the data, for example. So some of the use cases that you could imagine to build on top of NuCypher's proxy re-encryption would be things like end-to-end encrypted group chats. So building a group chat with proxy re-encryption is actually very straightforward. You could probably have a public key for some channel. All the messages get encrypted for that channel's key. And then you have a re-encryption key for each individual participant. So data gets re-encrypted on the fly for each participant. If someone gets banned or leaves the group, all you have to do is just delete the re-encryption key for that user, and they no longer have access to future messages. Another idea is to use proxy re-encryption and smart contracts to create decentralized data exchanges and decentralized data marketplaces. So for example, a decentralized Netflix where you're streaming encrypted data or encrypted video streams, and you only want to give people access in exchange for payment. You can also imagine basically any condition that you can embed into a smart contract, you can condition access on. So things like granting people access only within a specified time frame, or if there's a good Oracle solution, we can condition access on events pegged to the outside world. As just a few examples. Some of the other, I think, newer cryptographic techniques are things like ZK snarks and Zcash. So you can use ZK snarks to prove certain things without having to reveal the data. So in the case of Zcash, you can prove that you have the private key to certain coins. Monero is solving this idea of private transactions in a different way with something called ring signatures. So this is the idea of creating a special signature by grouping together many different potential signers. So you're obfuscating really who the actual transmitter of a transaction is, or who the ultimate authorized signer is. In this actually trusted execution environment, probably most famously popularized by Intel SGX, this is not actually a cryptographic technique, but I think it's worth mentioning because it's gotten a lot of attention lately. And this is the idea of running nodes on trusted hardware. So there's something called a secure enclave, where you can actually run pretty much arbitrary computations with the memory, with the data encrypted in memory. And I think this is very interesting because it allows this idea of generalized computations, but ultimately you're having to trust the hardware provider. So this is, at least for most of what we do at NuCypher, kind of out of scope, given that we're focused on the software side and the cryptography side. I think a very interesting approach that a couple of projects are working on is something called secure multi-party computation. And this is the idea that instead of running computation on one node, you just split that computation across many nodes. So no one node has access to all of the data. Like TE, SMPC is super interesting because in principle, you could do generalized computation on encrypted data. I think in practice, given that it's an interactive protocol, meaning that the nodes have to interact in order to finalize a computation, there's still a significant amount of sort of scientific advancements and performance improvements that need to happen. And given that interactivity, I don't know that it's ever really going to be a suitable solution for sort of these generalized performance sensitive computations, given the network overhead and the latency involved. But I think definitely a very interesting approach, and I think one that there are probably 3 or 4 projects actively working on. I would so now that's sort of the current landscape. Obviously a lot of projects and other techniques that I don't have time to touch on, but just to give you kind of a survey or landscape. And then looking forward, I think there's this idea of something called fully homomorphic encryption, which it's unclear kind of if it's actually achievable, but would be super interesting if we were able to solve. So this is the idea that you could actually run general computation and processing on encrypted data. You homomorphically encrypt some data, and then you're able to apply functions to that homomorphically encrypted data, get some homomorphically encrypted output, and then decrypt that output. So this actually opens up some super interesting use cases. You can imagine people building decentralized data exchanges or data marketplaces where, let's say, someone has aggregated a bunch of healthcare data or genomics data, say via some sort of hospital consortium. The consortium is able to monetize that data by selling the ability to run training models or process these computations against that data without ever exposing any of the underlying plain text. The problem with homomorphic encryption, I think, is similar to MPC in that it's not, there's significant performance improvements that need to happen before it becomes practically usable. One of the benefits of homomorphic encryption versus MPC is that it's non-interactive, so it doesn't have that same network overhead requirement for nodes to communicate with each other as does MPC, but it does have its own performance limitations. There are, beyond performance limitations, there's also this characteristic or something called ciphertext expansion. So you homomorphically encrypt data and run computations against it. The ciphertext can get extremely large. And then also it's not clear what the actual security characteristics or the security properties of homomorphic encryption are, given that you're actually modifying ciphertext. And if you think back to the slide where we talked about searchable encryption, generally when you're modifying ciphertext or you're trying to get this usability out of it, the trade-off is generally security. So that's an open question. At NuCypher, we've actually been putting a significant amount of research and resources towards sort of this as a longer term research goal for us, is to sort of identify what the security properties are, see if there's a way to apply FHE to smart contracts. You could have homomorphic smart contracts. But again, this is quite far out. But if it's able to be cracked, I think this could solve this sort of privacy trilemma, so solving the trade-off between privacy, usability, scalability, and decentralization. So I'll pause. If you want more information on NuCypher, our website is NuCypher.com. One of the things that we do as a company is all of our development is in the open and open source and in the public. So if you want to check out our GitHub, you can see our reference implementation of threshold proxy re-encryption, which is called PyUmbral. We have a private testnet, which we call MockNet, which you can check out on GitHub as well and use. We'll have a public testnet where anyone can spin up nodes and join the network very soon. All of our development discussions happen also in public on Discord, and that's also generally the quickest way to get a hold of us if you have questions or you're trying to build something with NuCypher. Our technical and scientific white paper is also on our website. Again, I'm on Discord, but if you want to email me, I'm just MacLane@NuCypher.com. So I will wrap it up here and open it up for questions if there are any.
Awesome. Thank you, MacLane. That was an incredible presentation, and we all learned a lot. Very clear and concise communication style, so I think we all appreciated that. Why don't you leave this slide open for just a few more minutes? That way people just can take note of those URLs in case they want to visit and learn more. And in the meantime, why don't we go ahead and take some audience questions? So the first question is from Kapil, and he says, awesome slides, can you share, please? So maybe one of your team members at some point could post a URL for that in the chat room at some point in the future, maybe?
Sure.
Does that sound fair?
Yeah, I think that's fine. Or I will upload them to our Discord afterwards, or if I still have access to the chat, I'll throw them in here afterwards.
Great, awesome. And the next question is from Jerry, which is, will NuCypher allow the capability for one sender to send 1 million anonymous messages or transactions on a public blockchain? And would you say that they are exercising their right to privacy?
So maybe I will just sort of clarify between messages and transactions. So NuCypher isn't enabling private transactions in the same way that something like a Monero or a Zcash would. We're focused on data privacy. But yeah, if you had, let's say, take our Telegram chat, for example, which has, I think, 40-something thousand people in it. If you were to try to encrypt that using NuCypher, you would just create 40,000 re-encryption keys. And this re-encryption operation is actually super lightweight. It's just elliptic curve cryptography, so it takes under a millisecond to do a re-encryption. You could have a very high throughput system built on NuCypher where you're doing tons of re-encryptions at a very fast pace, but we're not enabling private transactions in the sense that we don't enable you to send like ETH or Bitcoin in a private way.
Great, thank you. All right, the next question comes in from Stephen Rusi, who says, what can you do to deal with eventual attacks on encryption over time? I can record all the private data as part of the decentralized system and wait some years before an attack makes the current encryption vulnerable, and then start decrypting everyone's social security numbers. In this case, there's no evidence like there is when there is a breach in a centralized system. Any thoughts there?
Yep. So I think in general, we would advise not to actually store the encrypted data like on a blockchain. Technically you could, but generally for this reason, and also just for practical performance reasons, you'd want to store the data on something like IPFS or Swarm, where it could eventually be deleted. I also think that we've been very diligent in the sort of cryptographic primitives that we choose to build NuCypher with, as the defaults like SHA-20 is the block cipher, the elliptic curves that we use that are hopefully relatively future-proof. But even then, like it's also best practice to relatively frequently, at least probably annually, rotate the keys that the data is encrypted under, which actually you can also do with NuCypher.
Great. Next question is, what do you think about current quantum-resistant encryption schemes? And maybe you can preface that by talking about the potential threat of quantum and how you think about that.
Sure. So I think it's, so I guess one, I don't know that it's a huge priority today, because I think in practice we probably have, and I think as an industry, the sort of industry consensus is that we have quite a ways to go before quantum computing starts breaking a lot of the primitives that we built these different cryptocurrency and blockchain systems on top of. That said, I think I mentioned in the presentation SEC P256K1, which both Bitcoin and Ethereum use and that we use as well, is not quantum resistant. So if eventually we'll probably have to think about how we do that upgrade as an industry and as a community. Interestingly enough, proxy re-encryption, which I can speak to the best, there is actually a quantum resistant version of proxy re-encryption, which our cryptographer David Nunez previously invented, which is NTRU, or based on the NTRU encryption algorithm. So there is a path for us to do that upgrade if it becomes necessary.
Great, thank you. Next question is from Kapil, who asks, what are some use cases of proxy re-encryption? And are there any projects that are using the technology already?
Yep. So we, I guess, fundamentally view NuCypher proxy re-encryption as a horizontal infrastructure for anyone trying to manage private data with their decentralized application. In practice, where we've gotten the most early traction and early use cases are in healthcare projects like MediBlock, IRYO, Wholesome.io, that are trying to build patient-controlled medical record systems. So giving patients control over their own medical records and over the private keys that encrypt those medical records, while giving them the ability to actually still share those records with a healthcare provider or a doctor. NuCypher is also the access control layer for a lot of the new decentralized databases like Bluzell and Wolk, so enforcing who can and cannot query against those databases. Origin Protocol is also one of our partners. So they're the sharing economy protocol, and they're using it eventually as a way to sort of conditionally reveal certain information. So conditionally reveal the address of a booking on like a decentralized Airbnb type platform only once the booking has been made. I think also this idea of end-to-end encrypted group chats is a very good use case for NuCypher. I
agree. I want to highlight that second to last use case that MacLane just brought up, the idea of the decentralized Airbnb. If you could imagine an Airbnb on the blockchain where you want to make your personal address available only to those who actually rent your apartment. You don't want to make it available to everyone, because what if someone's stalking you and tries to find your address that way? So this ensures that it's only when a payment is made that you're actually revealing your address. And that's like a good analogy that I use to think about your technology. So great, thanks. Next question is from Alexander, who asks, how do you generate re-encryption keys in case of low-power devices? For example, if you have to generate a separate re-encryption key for every new potential receiver, that could be a problem for devices like dumb sensors.
Yep. So I would probably say that the current version of NuCypher is probably a little bit too heavyweight for low-power devices and for some of the IoT use cases, although we are working on making it more usable and more appropriate for that. But in general, this creation of re-encryption keys and also the re-encryption function itself is very cheap computation. It's just elliptic curve cryptography. So I think there is a path for us to do that. And then if you're building a system where you're streaming encrypted data from a bunch of devices, there's probably also a lot of engineering stuff you could do just to sort of solve that as well, as opposed to doing it at the protocol level.
Great, thank you. Let's see here. There's a couple questions that are kind of related here. Are we not in danger of going backwards, where the rich and powerful will be able to buy their privacy once again, to the detriment of the everyday populace who has more to fear from the rich people's secrets? More of a political question than anything. What do you think about that?
Yeah, I mean, I think it's definitely a valid argument, and probably to a large extent is this situation that we have today, where most people give up their privacy in exchange for convenience. And I think what our mission is at NuCypher is to provide very secure, very well engineered, very easy to use tools to developers, so that they can create equally convenient and equally compelling applications that provide a valuable service, hopefully in place of some of these centralized providers that we use today. So I think that's one of the interesting things about like Origin and a lot of the other projects that are building on NuCypher is that's a big part of the motivation for a lot of the projects and a lot of the apps being built in this space. And we view our role as the infrastructure provider who makes it easy to implement those privacy preserving technologies correctly and safely and securely.
Great, thank you. We've got a question from Nasir who says, best session of the day, MacLane, you are great. And that is his entire question. So thank you for that, Nasir. I'm sure MacLane appreciates that. How do you make money and how do we invest in the project?
Sure. So I actually didn't talk really much about our protocol, but NuCypher is a decentralized network of nodes that will be providing this re-encryption service. And if you want to be a node, you have to stake our token as a form of collateral or kind of a bond. And that gives you the right to then work for the network. And nodes get paid by users. And we, as a company, will be retaining some of the tokens from our initial token distribution, and we will be staking and running nodes ourselves. So we'll be one of many nodes, probably a relatively large node operator, but otherwise we'll be on equal footing as any other node provider.
I have a confession to make, which I will be running a node as well, because I believe in this project. It will not be as big a node as MacLane's node. We'll take one last question from Cloud Dev, which is, how does NuCypher's multi-user chat system compare to mainframe Onyx, which is surveillance resistant focused, and versus Promether Contact? NuCypher seems to be more advanced from a privacy security perspective. What are your thoughts there? So I'm actually not familiar with Promether Contact, but I do know the mainframe guys. I think that's a cool project. So just to be clear, like we are just building this proxy re-encryption protocol and developer tools. So multi-user group chat is just an example of the type of thing you could build using NuCypher. At least as of now, we don't plan to build it ourselves. So I would characterize like mainframe and Promether as like potential users. So NuCypher would potentially be part of their technology stack. Great. And there's a few questions that I want to ask you as well, which is, so let's see. So in terms of the blockchains that NuCypher is compatible with, what is it compatible with today? Sure. So we have built NuCypher, at least the first iteration of NuCypher, on top of Ethereum. So our token is an ERC20 token, and we use it to coordinate the network via staking to run a node as a way to allocate work and as well as compensation for that work. And then we also use it as a way to ensure that nodes are behaving correctly using a challenge protocol or slashing mechanism. So if you stake and you commit to running a node, and then your node, for whatever reason, doesn't do its job, it goes offline, it becomes malicious and just starts returning garbage data, your stake is at risk of getting slashed. So it provides this basically economic incentive to ensure that nodes do their job correctly. That said, if for whatever reason it became necessary for us to move to another chain, we could save the state and move it to a different chain. We don't anticipate having to do that, at least right now. And one of the principles that we built NuCypher with is to make sure that we're not just the privacy layer for Ethereum DApps. So we are building it in a way that other DApps built on other chains will eventually be able to use NuCypher as well, as long as they're able to pay the nodes. That makes sense. And for those in the audience who might be interested in running a node, how do they do that? Are there requirements to run a node? And what do they get for running a node? And how hard is it to run a node? Sure. So there is kind of a minimum staking requirement expressed in some minimum amount of tokens. We're still working through like the exact parameters around what that minimum staking requirement is. And then on a hardware side, you could run this on commodity hardware. If you had a very small stake, you could probably even get away with doing it on a Raspberry Pi, although we'd recommend probably using something a little bit more powerful. But it doesn't require any kind of specialized hardware. You can run this on commodity hardware. The bigger requirements from a technical standpoint are availability of that node. So making sure that it's online and not constantly disappearing and coming back.
So you want something like a stable internet connection, and probably some sort of uninterruptible power supply is very important. And then in practice, particularly early on in the network's life, you're probably going to have some sort of technical know-how or technical competence in terms of installing and configuring and maintaining that node.
Great. And you mentioned that NuCypher has a staking coin as part of your answer there to the node question. What do you think about proof of work versus proof of stake, given that you've chosen a staking type of architecture for your system?
Sure. So I would say our version of proof of stake is not as complicated as a proof of stake for an actual blockchain would be. So I guess I would note that NuCypher is, while it is its own separate network of nodes, it's not a separate blockchain. So it's not having to process transactions. So while our proof of stake is very complex, it's not probably as difficult to implement as something like Casper and Ethereum. We're primarily using it, one, to coordinate the network, to allocate work, to allocate rewards, and also as a way to slash in the event of misbehavior. So there is a lot of sort of game theory that we have to work through and think through the different sorts of attacks and make sure that we're not exposing the system to malicious actors in that sense. But I do think our version of proof of stake there's a lot clearer path towards viability than perhaps some of the proof of stake for underlying blockchains. I think it's very obvious in general that proof of work is far more proven than proof of stake, and we have 10 years of proof of work versus so far very little in production for proof of stake. That said, I'm very optimistic. There's a lot of very smart teams working on it. Most of the newer smart contract platforms and blockchains are based off of proof of stake from the get-go. We'll start seeing a lot of those go live either on testnet or even mainnet this year in some cases. And so there's a lot of very strong projects actively working on it, and I think there's a very obvious incentive for us to get that working as an industry.
Mm-hmm. That's great. And how fast is the re-encryption? Does it slow down your application at all? And is it practical for applications that are real-time where speed is super important?
Yep. So Proxy re-encryption itself is a very cheap computation. It's just elliptic curve cryptography, so really under a millisecond for a re-encryption. Given that it's a decentralized network, the bigger overhead is probably going to be things like latency. So waiting for the nodes to reply and doing these round trips between the data recipient and the nodes in the NuCypher network.
Great. And then last question for me is, you mentioned this cool vision of fully homomorphic encryption. Let's say that does come to fruition someday. Are there any negatives to that paradigm at all that we should be aware of?
I mean, I think the big open questions are, one, if it'll be possible for us to get FHE performant enough to use in practice. We've actually done some work around accelerating a couple different FHE libraries using GPUs, and we've actually got already 100x performance improvements there. There is still a ways to go. There's also the problem of ciphertext expansion. So in addition to performance, you could have ciphertexts that get unreasonably big. And then there are open questions around the security properties of homomorphic encryption. So even if we're able to get it very fast and reasonably sized ciphertext, it's not totally clear if you can implement it, let's say for homomorphic smart contracts in a secure way.
Got it. Thank you, MacLane. It's been very insightful. And audience, if you want to grab their slides, feel free to join their Discord server or visit any of the URLs displayed on the screen right now to learn more about NuCypher. MacLane, it was a pleasure having you here. It was very, very enlightening, and we're grateful for your time today.
Awesome. Thank you. Thank you, everyone, and thank you, Ed.
Great, thanks. We'll be right back with the CEO of the Origin protocol, who's going to give us a tutorial on kind of how to build a marketplace and a market network on the blockchain. So hang in there. We'll be right back.